Hello friends, welcome back to NPTEL online certification course entitled Soil and Water Conservation Engineering. I am Rajendra Singh, Professor in Agriculture and Food Engineering Department of IIT Kharagpur. We are in lecture 7, week number 2, and the topic today is erosivity and erodibility. Just to give you a background of what we are covering this week, in previous lecture we saw how to estimate soil loss, and during that process we went through universal soil loss equation, where we saw that rainfall erosivity index and soil erodibility index are two important factors, and in lecture 7 today we will be covering erosivity and erodibility. In lecture 8, we will see modifications in universal soil loss equation, that will be part 1 of the lecture, and in lecture 9 we will continue with that same modification in universal soil loss equation, that is part 2, and in last lecture of the week, that is lecture 10, we will go through soil loss measurement. So, coming to erosivity and erodibility. Now, just to remind you, I would like to write the equation which we saw for universal soil loss equation, that is, this is what we saw: A equal to R K L S C and P, and we defined R as rainfall erosivity index and K as soil erodibility index, and that is what erosivity and erodibility is our topic today. So, basically if you remember the process of soil erosion, we know that there are three processes. Water erosion, basically if we talk about detachment, transportation and deposition, these are the three processes. So, the first one is detachment, of course, and we also saw that it is the raindrop impact that is responsible for detachment in a major way. So, that ability of rain to detach the soil particles is referred to as erosivity, wherein on the other hand the susceptibility of soil to withstand against the raindrop impact, that is referred to as erodibility. So, that simply makes it clear that erosivity is a rainfall characteristics, and that is why R is defined as rainfall erosivity index, where erodibility is a soil characteristics, and that is why when we define K, we write soil erodibility index or soil erodibility factor. And soil erosion obviously occurs when rainfall erosivity exceeds the soil erodibility. Whenever erosivity will be greater than the erodibility, soil erosion will take place. Now, erosivity is the potential ability of rain to cause erosion, and it depends on several rainfall characteristics, that is rainfall intensity, drop size distribution, that we know that it is the kinetic energy which is responsible for raindrop impact. So, obviously, if the drop size is larger, then the impact will be much higher. Then terminal velocity, which again depends on the drop size. Higher the velocity, more will the kinetic energy. Wind velocity, because we know that we saw that when we saw the impact of wind, we saw the wind could change the direction of direction at which the raindrops hit the soil surface, and that could make a angle which might make erosion process or detachment process more severe. Then of course, the direction of slope will have the same impact. So, if the direction of slope we saw, if the soil is like this, if rainfall is vertical, then obviously this will be, the detached soil particles will move much larger down the slope as compared to up in the up direction. So, these are some of the factors on which erosivity primarily depends. Now, estimation of erosivity from rainfall data is basically could be done by two methods: EI 30 index method or KE greater than 25 index method, and we will see both these methods one by one. So, coming to EI 30 index method, this method was given by Wismir in 1965. We remember Wismir and Mispit They were responsible for giving the universal soil loss equation, and it was the Wissmeier that who gave the EI30 index method. And obviously, it is the name itself suggests it is computed by the product of kinetic energy of a storm and 30-minute maximum rainfall intensity, that is E represents kinetic energy of the storm and I30 represents the 30-minute maximum rainfall intensity, and introduced this in previous lecture also. We saw that when we discuss R, we say R is EI 30, or we also said is that it is Ke times I 30. So, that means E or K is the kinetic energy and I is the rainfall intensity. Suffix 30 represents the 30 minute duration during the storm where the rainfall intensity is maximum. So, it is referred to as defined as 30-minute maximum rainfall intensity. Now, relation between kinetic energy and rainfall intensity is given by Wissmeier Smith in 1958, is given by this equation, that is E equals to 0.119 plus 0.0873 log base 10 I, where I is the E is the kinetic energy in megajoules per hectare millimeter and I is the rainfall intensity in millimeter per hour. And like any other empirical equation, as I have mentioned also, that we have to be careful about the units if we want to use the equation in its present form or its given form, because the coefficients or constants which are there, they are because of the units which are being used for variables. So, that means, if you want to use this Wissmeier Smith equation, I has to be put in millimeter per hour and E will always be, the output will always be in megajoules per hectare millimeter. So, we have to remember the formula. Now, rainfall erosivity index, as I already said, that is given by EI 30 equals to kinetic energy times I 30, and please note here that E, which is given in, which is used in Wissmeier and Smith equation, and Ke, which is being used here, they are equivalent, they are the same. So, E or Ke, when we are writing, we are talking about the kinetic energy and I 30 remains I 30. So, that is A R is E I 30 or Ke I 30, and both kinetic energy and I 30 are obtained for a rainfall events, because the rainfall characteristics. So, obviously, we have to obtain for a particular rainfall event, and for identifying a particular rainfall event, we use the rain gauge chart. So, it is basically the rain gauge chart which comes from a recording type rain gauge that is used for finding out the both kinetic energy as well as I 30. So, this example here you see, this chart here you see is a typical rain gauge chart which is obtained from siphon of float type of recording rain gauge. I am sure that you have read various kinds of rain gauges, non-recording, recording, and within recording you probably have heard that there is a tipping bucket, there is a weighing bucket, and there is a float or siphon type of rain gauge. So, this is the siphon or float type of rain gauge, that is basically the standard recording type rain gauge adopted in India, and that is why I am showing the chart here. So, in this case, as you can guess, that is a float type and siphon type, the terminologies are used because there is a float chamber in which the rainfall gets collected, and as in the chamber, it is a cylindrical chamber basically. So, as the water level goes up, there is a float here, that float rises, and this float is connected to some kind of recording mechanism here, and in this recording mechanism there is a chart place. So, that is why you see that it is the maximum 10 millimeters of rainfall, that is the capacity of the float chamber. So, here this chart shows this starts at 8 o'clock, because typically in India 8 o'clock 8 a.m. is the time where the rainfall is recorded, is supposed to be recorded by as per IMD. So, that is why this chart also starts from 8 o'clock. So, here this line shows that the rain gauge event, the rainfall event is starting on 8 o'clock, and then this continuous recording is there. At this point you see it is around 12 o'clock, that is the noon time, the total rainfall is becoming 10 millimeters. This is 10 millimeter, this scale is 10 millimeter. So, this is becoming 10 millimeter, that means the capacity of this float chamber is completely filled, and then the second part of the name comes, that is siphoning. Siphoning takes place, and that means this recording mechanism comes back, or float comes back to 0 level, and then again recording starts. So, that simply means here you can see that here siphoning has taken place, but immediately there is a continuous record. That this simply shows that there is a rainfall event over this period of time. So, 8 o'clock till almost 2:30, this is 14:30 actually, 14:30. So, from 800 hours to 14:30 hours there is a continuous rainfall, and then from this rain gauge chart we can also read what is the magnitude of rainfall. So, this is 10 mm, and here as you see this is 6 mm. So, that means during this period total 16 mm of rainfall occurred. So, that is one rainfall event, and then after this 14:30 hours till 24 hours we see a horizontal line which shows that there is no rainfall occurring, and then again this pen starts raising, or the float rises, and because of that there is a change. So, that means you see here from 24 hours till 5 in the morning there is a, this reaches the capacity, that is 10 mm, this is 6 mm, this is 10 mm. So, that means from this to this place it represents in this period 4 mm of rainfall, and then siphoning takes place, and then again the pen starts up and goes here. So, that means in this is the second event, and it is continuing till 6 a.m. So, that means the total duration of storm here is 6 hours, and the total rainfall which is occurring here is 4 and 4 8 mm of rainfall. So, in this particular day, or on this particular day for which this chart is taken, there are two rainfall events. One is continuing from 8 o'clock in the morning till 2:30 in the afternoon and having 16 mm of rainfall, where in the second event is starting at 12 midnight continuing till 6 o'clock in the morning, and total rainfall is 8 mm. So, this is how we can identify a particular rainfall event, and this is how we can calculate both kinetic energy as well I30 from a given rain gauge chart. So, from the rain gauge chart just now we saw we identify the event. So, basically we isolate the event, and then kinetic energy and I30 are estimated. So, here you see while estimating the kinetic energy, the entire rainfall event is being used. So, entire rainfall event is being used here for calculating the kinetic energy, wherein for estimating the I30, as the name itself suggests, we have to really look into the entire storm and look for the slot where 30-minute slot or 30-minute duration where the rainfall intensity is maximum, and that is why it is defined as maximum 30-minute intensity during the event. So, let us take an example. So, this particular example following rainfall event is isolated from a rain gauge chart. Calculate the rainfall erosivity index. So, here you see a particular date is given, different starting times, shifting times is given, time interval is given, reading at start is given, reading at shifting time is given, and rainfall magnitude is given. So, from here for different intervals we know what is the rainfall taking place. So, basically this data has come from a rain gauge chart. So, using this data we can really go and estimate the EI30 or rainfall erosivity index. So, what is done here is you can see that we have rainfall in millimeters duration, rainfall in millimeters given. So, we can calculate for each duration rainfall intensity. So, that is column 2, that is the rainfall, divided by column 1, that is the duration 20 minutes multiplied by 60. So, that we can get in unit desired unit of millimeter per hour. And once we know the intensity, then we can use the Smear and Smith equation, which is a function of I. So, knowing I, using this equation we can calculate the kinetic energy in million joules per hectare millimeter quite easily. So, that is what we have done here. So, for each for this I, this is the kinetic energy in megajoules per hectare millimeter. But in this equation you remember the EI 30 unit is megajoules millimeter per hectare per hour. That simply means E is being used in megajoules per hectare and I 30 is in millimeter per hour. So, that simply means the kinetic energy which is there in megajoules per hectare millimeter, that has to be converted into this unit megajoules per hectare. So, for that we multiply column 4 with column 2, which is column 2 is nothing but the magnitude of rainfall in different durations, in order to get the kinetic energy of rainfall in desired unit, that is megajoules per hectare for different intervals. And then the total sum is obtained by adding these values, which is 4.59 in this case, which is basically which has to be used in this equation. And then that means kinetic energy we have calculated. The next important thing is to calculate the I 30, and for I 30, first thing is that we have to, within the time frame, we have to identify 30 minute durations. So, here if we analyze one by one, we see that there are we see here that there are 3 different events we can identify of 30 minute duration, 22 plus 8 is 30, 8, 10 and 12 is 30. And in each of these 30 minutes we can calculate what is the total rainfall, 3.3 mm, here 12.2 mm and here 10 mm. So, from this we see that this duration is, that is the 30 minute duration where the intensity will be maximum, that is because 30 minute duration rainfall is 12.2. So, that means the maximum intensity in continuous 30 minute duration is 2 times of that, that is 24.4. So, that so I 30 maximum for this particular problem is 24.4 millimeters per hour. And once we know K I and once we know when we know the K E and once we know I 30, then obviously the multiplication of this sum value here, the sum value here and the I 30 value here will give us the total rainfall erosivity index E I 30 for this particular event or for that particular problem. So, that is how we estimate the E I 30 for a given event. We can take yet another problem. Let us say for example, the following mass curve reading was taken from a recording type rain gauge to analyze the rainfall. Time since beginning of storm is given here, that is different 4, 420, 4 to 520, that is the duration, and cumulative rainfall values are given here 0 here, that means here the rainfall event starts and the total rainfall is 33 during this period, and we have to calculate the rainfall erosivity index. So, just following the procedure we saw earlier in the earlier example, we can do that. So, here obviously for different times, different time intervals, we know what are the cumulative rainfall values. So, for different durations, so here 4 to 420, that means 20 minute duration, the magnitude of rainfall is 1 mm. So, for different durations we can find out what is the total amount of rainfall and thus we can calculate the intensity of rainfall. And once we know the intensity of rainfall, by using the Smith and Smith equation, we can calculate kinetic energy in megajoules per hectare millimeter, and then again by multiplying this with the total magnitude of rainfall, we can get in the kinetic energy in megajoules per hectare. That is what we want. And then next part of this problem is to be able to estimate the I 30. That means, we have to again find out different continuous 30 minute durations, and here again we see that there are 3 different events. So, these events are, as you can see here, 1, 1, 2, 3 different events are there, that means 30 minutes continuous duration, and rainfall in these 30 minutes we know 9 mm, 27 mm and 23 mm. So, again this one is 30-minute duration where the intensity is maximum and total magnitude of rainfall is 27 mm. So, that means intensity I 30 maximum is 54 millimeters per hour, and once we know the kinetic energy, the sum and I 30 multiplication of these two will give us the EI 30 or rainfall erosivity in megajoules millimeter per hectare per hour. So, that is the answer which we are looking for this particular problem. Now, we come to continue with erosivity further, and here we are going into the next method, that is KI greater than 25 index method, KI greater than 25 index method. So, the EI 30 method, just now we saw how to calculate the rainfall erosivity using the method. This was basically developed under American conditions, which may not be suitable for tropical and subtropical zones. So, that is the drawback of EI 30 method as far as its development conditions are concerned. So, to overcome that drawback, Hudson in 1981 he developed KE greater than 25 index method, and this was meant for computing the rainfall erosivity of tropical storms. So, the first method which was given by Smear and Smith, that was based on American data, and that was said that it may not be suitable for tropical and subtropical zones, and that is how this new method came, K greater than 25 came. And in this method, erosion takes place only at a threshold value of rainfall intensity, and the logic is given in the as follows, that is the threshold value first which is used of rainfall intensity is 25 millimeters per hour, which is determined based on experiments. So, based on a large many experiments, the threshold value of rainfall intensity is obtained as 25 mm per hour, and that is why the name of the method KE 25 index method. That is, it is assumed that rainfall intensities which are less than 25 millimeter per hour do not yield a significant soil erosion, hence this method is called K greater than 25 index method. So, in the experiments which were conducted in tropical conditions, they showed that if the rainfall intensity is less than 25 mm per hour, then the soil erosion was not significant, and that is why it was said that the threshold value of rainfall intensity is 25 mm per hour for causing erosion, and that is why this method K is greater than 25 index method. The estimation procedure of this method in EI 30 is very similar. Only difference is that in EI 30 method we calculate kinetic energy for all intensities of rainfall, where in this case Ki is calculated, Ke is the calculated, that kinetic energy calculated only if I is greater than 25 mm per hour. So, any rainfall intensity in any duration where the rainfall intensity is less than 25 mm per hour, that is neglected basically in this particular method. So, let us take a problem to really see how to use this. So, it is the same problem which was used for applying the EI 30 method. So, now in the same problem, where the following mass curve reading was taken from a recording type rain gauge chart to analyze the rainfall, where the rainfall begins at 4 o'clock, continues till 5:20, and the cumulative rainfall during the event is 33 mm. That same event is being used, and we have to calculate the rainfall erosivity index using the Ke greater than 25 index method. Earlier we used EI 30 method. So, now we are using Ke greater than 25 index method. So, here is the solution. So, here again the time since beginning will be there, cumulative rainfall will be written as it is, and Duration of course remains the same, there is no change, that is 4 to 420 20 minutes. Then rainfall is 0 to 1, that is 1 mm. Then in 2027 7 minutes, rainfall is 2 mm and so on. So, all those calculations remain the same. The data extraction from the rain gauge chart or rain gauge data which is given in tabular form remains the same. Intensity value calculation is also same. So, we calculate till intensity, there is no change, the procedure remains the same as it was in EI 30 method, but this difference starts from here. Here in any duration, if rainfall intensity is less than 25 mm per hour, then kinetic energy is not calculated. That means, kinetic energy is calculated only if I is greater than 25 mm per hour. So, in this event you see which is less than 25 mm per hour, we are not calculating kinetic energy. Similarly, here it is 17.14, it is less than 25 mm per hour. So, we are not calculating kinetic energy. So, only those events or those durations where the intensity is more than 25. So, 1, 2, only 3 durations where intensity is greater than 25. So, we are calculating, rest of the places we are not calculating. So, that is how you see only 3 values in the kinetic energy, that is megajoules per hectare millimeter, which comes from the Wishmeyer and Smith equation. Same equation is Wishmeyer and Smith equation is used here also for calculating the kinetic energy. And obviously, then megajoule it will be expressed in megajoules per hectare also only for these durations. So, that simply means that only these kinetic energies will be multiplied by the rainfall amount, and that is how these values will come. So, the total sum will be 7.428. Remember, in EI 30 method we used or we calculated kinetic energy for each of these durations. So, obviously, this sum was larger. I 30 calculations remains the same. So, that is why we in this case also will get 54 mm of rainfall intensity mm per hour, and obviously, EI 30 value will be then multiplication of these two to obtain this. So, in this case the difference is that in the previous case the sum was the kinetic energy sum was 8.698, here it is 7.428, and that is why EI 30 which was 470 megajoules millimeter per hectare hour, that is now getting reduced to 401, because we are only considering I greater than 25 mm per hour for calculating the kinetic energy. So, that is the only difference here. So, 2 methods, one is this method is said that is more suitable for tropical storms or tropical regions. Here we neglect the rainfall intensities, the durations with rainfall intensities less than 25 mm per hour for calculating the rainfall erosivity. That is the only difference, otherwise. So, procedurally we saw more or less both methods acts in the similar fashion. The next thing is erodibility, which is the soil's inherent susceptible to erosion, and this can be estimated using runoff plot or soil properties. So, as far as runoff plot is concerned, runoff from runoff plots is collected in a tank and its volume is measured, and for estimating the soil loss, the water in tank is churned thoroughly, so that the soil water mix is complete, and then from this tank we take out a sample of 500 to 1000 cc, that is half liter to 1 liter sample is taken, and this sample is taken to laboratory, where we find out the amount of soil in the sample in grams per liter, that is 1 liter. So, how much grams of soil was there. So, that gives us the total soil loss in grams per liter, and then for soil loss from the plat, soil loss grams per liter that we have obtained in laboratory, total runoff volume we have already calculated in liters. So, this will give us soil loss in grams. To convert that in ton, which is the normally unit, we multiply that with 10 to the power minus 6. So, in this way we get soil loss in tons, and then soil loss per hectare, which is not usual unit is tons per hectare, soil loss in tons divided by area of the plot in hectare, that is from where the sample has come, that will tell us give us soil loss per hectare in tons per hectare, and that is how erodibility can be found out experimentally. Basically, this is experimental determination using the runoff plots. In the second case, we basically find out erodibility, or rather we can still adjust this for soil loss for LS factor, because we have used a non-standard, we might have used a non-standard plot. So, for that we convert that to standard USLE plot, where we knew that we know that the slope 9% and length of 22.13 meters is used, and this plot is continuously fallow till up and down. So, for that we adjusted soil loss, which is soil loss per hectare, which we calculated earlier, divided by LS factor. So, divided by rainfall erosivity index, that will give us the soil erodibility value, and rainfall erosivity index calculation already we have seen how to estimate that. So, from using this soil loss values and the rainfall erosivity values, we can find out what is the soil erodibility for a given experimental data. Alternatively, we can also use the soil properties for estimating the erodibility, and basically we use the soil properties like percent sand, percent silt, clay and organic matter, and then this empirical equation is used here, where you see that capital M is particle size parameters, that is percent silt plus percent very fine sand multiplied by 100 minus percent clay, and this when we do the soil texture analysis, all these values we can get from laboratory. A is percent organic matter, which can also be obtained from laboratory. B, the soil structure code, and this code is very fine granular for 1, fine granular for 2, medius of coarse granular 3, block, platy and massive 4, and C, which is used here in this equation, is profile permeability class. So, if the permeability is rapid, then it is 1, medium to rapid 2, moderate 3, slow to moderate 4, slow 5 and very slow 6. So, using B and C codes here and knowing the percent sand, silt, clay and organic matter, which can be obtained from experiments from the laboratory, we can also determine K using this empirical equation. So, erodibility can be estimated by two methods, using the runoff plot for experiments, and also by using the soil properties using the empirical relationship. Similarly, we saw for rainfall erodibility we have two methods, one is EI 30 method and one is K greater than 25 index method. So, with this we come to end of this class, where we have seen how to estimate rainfall erosivity as well as soil erodibility. Thank you very much.